dans les 30 secondes. Ok, donc excusez-nous pour ce petit retard. Le premier exposé cet après-midi est fait par Maxim KONTSEVICH, Derived Grothendieck-Teichmüller Group and Graph Complexes.
Okay, thank you. Yeah, so I will speak about pretty abstract and hard to follow topics, but I want to say that it actually will have something very concrete behind it, and I will start with examples of what I will call zeta of 3 flows. Zeta of 3, it's value of a Riemann zeta function. And what is this flow? Yeah, there are actually two formulas. The first formula is like this. Suppose you have a, in Rn, you have a Poisson structure. X is suppose it just it starts to just this bivector field, and I want to write evolution equation for this bivector field with respect to time. So, so this zeta of 3 flow will be the following, and this is called P dot, and sorry, it will be a bit long formula. Sum over ij, and then sum over K, L, M, K prime, L prime, N prime. All variables grow from 1 to capital N. Then take D3, Pij, dxk, dxl, dxm, dk prime, dxl prime, dp, l prime, dxm prime, p prime over dxk prime times di times dj plus a second term. What is it? 6 times, so again somewhere im, so it will be different letters, and then sum over j, k, l, j, l prime, k prime, l prime, and m prime. Okay. Certain nice differential equation. There are two things I can say about this equation. First, it's interesting equation because it has interesting property. The property is, the theorem is the following. If, so it's p dot will be dt with respect to some time variable. If at time equal to 0, p is Poisson bracket, then it's Poisson bracket for all times, at least when consider analytic solutions.
P dot equals 0?
Sorry?
P dot equals 0?
So p dot? Sorry?
P dot is 0.
No. If it's Poisson bracket, it means that its bracket with itself is equal to 0. There is some Schotten bracket is equal to 0 for t equal to 0. Then the same will happen for all time. And second property is that if you start with a Poisson bracket and change variables. You get different family of Poisson brackets, but again, each time they differ only by change of variables. For non-Poisson brackets, it's not true. Sorry? What is P naught? P dot is derivative with respect to some time. I consider evolution equation. Yeah. So. Sorry? No. I write on the space of Poisson brackets in Rn. I write evolution operator. So these things will be function of x and t, and derivative with respect to t given by some expression x. And the statement, if for time equal to 0, I have a Poisson bracket, then for any further time I also have a Poisson
bracket 0.
Sorry?
I have Poisson bracket meaning it is 0.
It means that the Schotten bracket of this bivector field itself is 0. It defines a Poisson structure. This bivector field defines a Poisson structure. And second statement, if you have a p at t equal to 0 is equivalent up to some kind of p tilde t equal to 0 up to change of variables. Then for any t, pt is equivalent to pt tilde up to change of variables. And both are Poisson brackets.
And if you dualize it in terms of symplectic structure, can you see it?
Sorry?
Dualize and look in terms of symplectic structure.
No, Poisson structure is not symplectic structure. It should be degenerate.
Degenerate.
Yes.
But if it's symplectic, it will degenerate.
Yeah, it's symplectic, nothing will happen. It will be kind of trivial flow up to change of variables. So it's a pretty amazing algebraic property. And so it looks like interesting equation, but also it's not interesting equation because I published 20 years ago, there's no kind of reaction whatsoever for anybody. Except a few months ago, Alexei Kiselov found that in an original paper I made a mistake if I forget about second term. Yeah. Yeah, so it means that nobody ever considered this thing, so it's probably not interesting. But in fact, it's I challenge maybe analysts to study what are properties of this flow. For example, is it well defined? And there are many mysteries. There's no examples up to no example up to now when this flow produces really genuinely non-trivial deformation of Poisson structure. For example, if it starts with symplectic structure, that's very easy to see that nothing goes on. Or you go in 2 dimensions, also nothing goes on. Yeah, so it's a big mystery. So what one can prove that by formal calculation, up to diffeomorphism, yeah. What one can prove is that if you kind of manipulate with symbols, this is not trivial deformation. You cannot prove that it's trivial by manipulating with symbols. Yeah, so it's a mystery what's going on. Is it really trivial deformation or not? We don't know.
Yeah. Symbols, it is non-trivial.
Yeah, no, it just kind of if you do kind of calculation in uniformal expressions, it will be non-trivial deformation. No.
In examples, it's trivial.
In all examples, it's trivial. Yeah. What could happen? Yeah, there could be some identity which is not provable by some means, but true by another means. Yeah, so it's kind of very mysterious.
No, the example probably is special. They have special features. The examples.
No, any examples which you can at least we can calculate. Not many people tried. Maybe 2 people.
Structure will be probably not trivial.
Sorry?
Take generic kind of Poisson structure.
What does it mean generic? You solve quadratic equations, so this thing it's not reduced. You get to different components. It makes no sense. Yeah. Now, so it's example of what concrete expression which come from all the signs which I will explain in a few minutes. There is a more concrete case of the zeta of 3 flow.
But locally, not trivial.
Locally, it's not trivial. Yeah, it's not. Yeah, it could be some singular point where the Poisson structure vanishes with some complicated way, and maybe it will be non-trivial deformation. There is another kind of example of zeta of 3 flow, which is one can easily see that it's non-trivial. It's the following. Let's X will be complex variety, complex manifold. Not necessarily compact It could be algebraic variety or non-algebraic. It could be open. It doesn't matter. So there are two vector spaces. There is a direct sum of cohomology of X with coefficients in forms. And there is direct sum of cohomology of X with coefficients in polyvector fields. So there is one space and another space. And there is a map, action of V1 by on V2.
You mean as coefficients?
Sorry?
Coefficients are forms.
Yeah, consider cohomology with sheaf of holomorphic forms. And here sheaf of holomorphic vector field. Holomorphic vector fields, yeah. Then there is a map action of one guy to another. So hi omega j multiplied by hp x which q t x will go to hi plus p x omega q minus j, which q minus j. You contract forms with vector fields, so you get this map. Now consider Chern class of the tangent bundle, which lies in the sum over hi x omega I. So I can write a sum over homogeneous components of dimension 2i. And then, for example, we get action of Chern 3 acting on V2 on cohomology of X which tangent to X to itself. Gets this operator. This thing, for example, is a commutative ring by cup product theorem. It is a derivation. It's also non-trivial theorem, and kind of eventually, if I want to reduce to something concrete proof, it will go to something like this. I never tried it, and here there is it's very easy to construct examples with this actions non. This operator action of Chern 3 is a derivation with respect to cup product. Also, one can put Chern 5, Chern 7. They're all derivations. Yeah, this is kind of identity in differential geometry. This is derivation with respect to cup product, and it's kind of another part version of this.
A compact manifold is universal? No.
Completely universal. Yeah, it could be any complex manifold. Yeah, so it's some differential geometric identity. Yeah. Sorry? No, this is a theorem. Yeah, it's a theorem. Yeah, no, both are theorems. I don't know what. No. These are related facts. I have to say that here. Yeah. Now that's it's a related facts, and yeah. So no, just I want to give you a feeling that what I will explain later, it's not completely abstract nonsense. There are concrete, hard corollaries. Yeah. Okay. Okay. Yes. So now I'll start.
This identity would look for germs. What does it mean?
Sorry?
If I will go to homology, work on the level of germs.
No, this thing, the right hand side, the second statement for germs means nothing. Yeah. No, because there's no high cohomology. There's no high cohomology of forms. Yeah. So all this are related to something called graph complex, which I will define later, and this Z203, Z205, and so on are related to Galois group of Q bar over Q. And what I claim that things are somehow related, and this will be some result of Willwacher, which I will explain you at the end of the talk. But before starting, I have to introduce some kind of general story. It's about operads. So what are operads? there's two notions. There are operads and there are algebras over operads. And algebras over operads everybody knows. For example, one consider fix a field, okay? And it will be convenient to have it characteristic 0. Then we can consider, for example, associative algebras. Or we consider Lie algebras. Or Poisson algebras. So it means that we have some notion of vector space with some kind of product and some identities with this product. And this can be encoded in some kind of general framework. Namely, for all such category of algebras, one have two functors, two vector spaces. Functor in one direction is you forget algebra structure. And then you get a joint functor, get free algebra generated by vector space. And if you go back and forth, you get end of functors of category of vector space. From vector space, you make, let's say, free associative algebra and forget about algebra structure. This end of functor, which you have on category of vector space, it's what's called polynomial. It will be polynomial functor. What does it mean? It's actually maybe better called form power series functor. It's a vector space goes to infinite sum from n equal to 0 to infinity. For example, for free associative algebra, we get v to tensor n. Or more generally, if you consider like free Lie algebra, it goes to sum from n equal to 0 infinity. You get certain space, Pn, tensor Qn, and you take co-invariance and the actual symmetry group, where P of n is a representation of symmetry group. Actually, what is it? So we get these polynomial functors, and the definition: an operad is monoid in category of polynomial functors. The category of polynomial functors is a monoidal category, so it can compose polynomial functors. So it's kind of general categorical nonsense that in such situation, when you get two adjoint functors and appropriate categorical properties, this category of algebras will be modules over this monad, or modules over this monoid. So you encode types of algebras by sequence of representation of symmetric group and some connecting morphisms. One can analyze what does it mean this operate in terms of representation of symmetric group. It turns out that you get essentially two maps, Kn, to have a structure of an operad on this polynomial functor or monoid. It's the same as to have collection of such maps, and also you get identity element to P1, satisfying certain identities. What in real life this Pn look like? For example, let's say Lie algebras. For the case of Lie algebras, the space P is denoted maybe kind of Lie n. It will be a vector space generated by universal Lie expressions in n variables, x1, xn. For example, for n equal to, what I can do in two variables, you just can do only Lie bracket. And if you permute, you get minus this, so action will be, in n equals 3, you get x1, x2, x3, and x2, x3, x1, for example. But the last one is a linear combination by Jacobi identity. It will be two-dimensional space. And for Lie algebras, the dimension of nth component is n minus 1 factorial. For example, one can put iterated brackets and put the last variable to be xn, something like this. Now, so that's that's the notion of operads, and not everything which you can express in linear algebra is an operad. There are more complicated things like Hopf algebras. These things are called properties, but I will not talk of them. Yeah, so there are operads, and for example, if you consider Poisson algebras, and let's say so, then corresponding space will have dimension n factorial, not n minus 1 factorial like for Lie algebras. Just to give you an idea what does this space look like. For example, for n equal 2, you can write in Poisson algebra, you can write two expressions. You can take product or Poisson bracket of two functional, some Poisson variety. For n equals 3, you can write the product consider such guys, and also you can write such expressions. The third one I will not write because it's by Jacobi identity is the sum. So you see you get the basis of expression has 6 elements, which is n factorial, which is the same as number of expressions, actually the same as dimension of associated n, when you just take product in all possible orders. And which corresponds to the fact that associative algebras are deformations of Poisson algebras, and also associative operad is deformation of Poisson operad. So there is this general theory of operads, but I just and there's for example, book of Ladé about operads, but what we really understand about operads are essentially these classical cases and some graded version. The version which will be important for me will be Gersten-Haber algebras. That's algebras in a slightly different framework. In all story about operads, we use category of vector spaces and make tensor product of vector space. So we replace vector spaces and the tensor product replaced by z-graded vector spaces. And also this tensor product, but with symmetry morphism we use causal rule of signs. And Gersten-Haber algebra is kind of cousin of Poisson algebra. It's z-graded commutative associative algebra, endowed with a bracket of degree -1, not 0. The product is of degree 0, but bracket is of degree -1. And satisfying essentially the same rules. The bracket is derivation with respect to each variable and satisfies Jacobi identity. So it's not a really unfamiliar notion because the basic examples are, the basic example is you consider section on any manifold, like some manifold, consider polyvector fields. On polyvector fields, we can have cup product and Schouten bracket, and the things which satisfies exactly Gersten-Haber algebra. Yeah, so that's a typical example of Gersten-Haber algebra, which is kind of a little relative of Poisson algebra in dimension of the space ger n is z-graded, but it again has dimension n factorial, but now it's kind of z-graded space. And this operator of Gastro hybrid algebra will be main hero for my talk. I will speak about this operator. But just before continuing, I want to say some very little story. Tell a very little story about that in this framework of operads or DG operads, one can or algebras, one can speak about some deformation theory. So the deformation theory, this deformation theory works in a still larger category. We consider complexes of vector spaces instead of Z-graded spaces. We consider tensor category of complexes of vector spaces. And then one can define operads in this world. Let's get some DG operads and DG algebras over infinite in both directions, yeah, over DG operads. One can speak about this DG algebras, or even usual operad in vector space can consider this complex in degree 0. So one can consider about DG algebras, DG Lie algebras by this story. And yeah, so there are kind of essentially two definitions one can make. First, one can make a notion of what's called quasi-free algebra for a DG operad. Let's say B. A quasi-free algebra is DG algebra. Let's denote, I don't know, something like A, and which is free if you forget differential, is isomorphic to free P of some vector space of generators as Z-graded space. And the property is the following. But differentials should behave in some kind of different way. The space of generators should be filtered by some pieces, and union of Gn is equal to G. And the property is differential of n space of generators adequate n problems belongs to subalgebra generated by Gn minus 1. Now, so these spaces could be infinite dimensional, but you should have this countable filtration. Yeah, so that's.
What do you mean by free P?
Sorry? No, free algebra. Yeah, because I have notion of free algebra for the operad. Yeah. When I yeah, so that's. Wait a second. Should I go? So it's one definition. Second definition, what will be a resolution of DG algebra? DG algebra now called B, is a quasi-free algebra plus a homomorphism from A to B of DG algebras which is a quasi-isomorphism. I recall that these DG algebras are particularly complexes, so these things should induce isomorphism of cohomology. Is of cohomology of complexes. And of course, there is a science called model category and so on, but kind of deformation theory and homotopy theory of DG algebras is the following. You just consider algebras up to this quasi-isomorphism and replace by resolutions. Kind of good models. Yeah, that's, it's very easy to prove that any algebra has a resolution, essentially kill step-by-step cohomology classes and do it countably many times and get some resolutions. Yeah, so the beautiful thing that for all classical operads, there are nice canonical resolutions, which we have here. Yeah, so it's, and how one can use these resolutions, so what will be general deformation theory? There are several things to deform. Suppose you get a, let's say, a morphism of DG algebras. And I want to develop some kind of deformation theory of the morphism. What will be so I want to define some kind of deformation complex, and deformation complex of F. And how one can proceed? One proceeds in two steps. First, one choose a resolution of B1 so it means that you can replace B1 by this free G, and then the complex will be the following. It will be Hom deformation complex will be Hom from G to B2. Because yeah, it will have a certain structure of a complex, but no, from G to B2. Sorry, no, I didn't. Because the space of homomorphism from G to B2 as vector spaces is the same as space of homomorphism of kind of algebras without differentials from, in appropriate sense, from A to B2. Yeah, that's the idea. Now, so what the structure has this deformation complex? It's called C. It's a priori just Z-graded space. The deformation complex, all these questions in deformation theory give something called Lie infinity algebras. Lie infinity, yeah, so this, the structure of deformation complex may say the following. This deformation complex shifted by -1 is Lie infinity algebra. The Lie infinity is certain DG operad, which is resolution of Lie operad. But this can be said in kind of geometric terms. So we get this complex, and the structure of Lie algebra up to shift 1, it's essentially the following. You consider C plus symmetric square of C plus symmetric cube of C, and so on. It's a co-commutative coalgebra. And this Lie infinity structure, it's a derivation of degree +1 of this co-commutative coalgebra square equal to 0. Yeah, so it's something hard to understand. One can try to think in the following way. If one take a dual space, kind of dual to completed symmetric algebra generated by dual space. And this looks like algebra formal power series on some z-graded supermanifold. And this Lie infinity structure means that you have odd vector field of degree +1 with square equal to 0 on this vector space. Yeah, this is kind of from point of view of supergeometry. What is Lie infinity algebra? It's just odd vector field with square equal to 0. And these things gives a functor on Artin algebras and maybe with values in simplicial sets. So that's a basic geometric object. And one can see without any calculation why you get this odd vector field on this space. The story is the following. When we interpret this space as a space of homomorphism of free algebra to another algebra. So it's some kind of maybe infinite-dimensional manifold. Or we consider formal neighborhood of certain map. Then the differential gives automorphism of this guy and automorphism of this guy. So it gives odd vector field on the space of maps, and square equal to 0 by tautological reasons, because it's equal to 0 this way. So this kind of very simple geometric meaning one can translate to formulas and produce certain complicated Lie infinity structure in explicit terms. Yeah, so that's how we get this deformation theory. And there's something pretty interesting in this picture. One can compare with the following situation. Compare with some topological situation. Suppose I have two topological spaces, X with some pointed spaces, this point X, and Y. I have two topological spaces. Then I have a space of maps from X to Y. It's again some space with base point because we have trivial map. And so we have space of maps, and now we want to calculate homotopy groups of M relative to base point. There is a situation in topology one can kind of approach it step by step. Suppose X is finite cell complex of dimension less than some capital N. And suppose that YY is, let's say, n plus 1 connected. Or maybe n, yeah, maybe n connected. It's sufficiently large connected. Then I claim that this thing is kind of doesn't really make perfect, doesn't make sense, but there exists a kind of convergent spectral sequence from what? You consider homology of cohomology of my space with respect to base point with integer coefficients. Reduce homology, so I don't consider H0, so it will be H1, multiplied by homotopy group. And homotopy groups I will consider placed in negative degrees as, because I will always, to keep sanity, I want to have differential degree plus 1 in all situations. So homotopy group will be kind of in negative degrees, placed in negative degrees of Y. And then it converts to homotopy groups of M. Yeah, that doesn't really make sense. Yeah, for example, in principle, to have pi 1, this non-abelian group, how you cannot make tensor product for non-abelian group with abelian, but this restriction do not allow it. But why it happens? If X is a point, then the space of maps is a point. Yeah, so nothing to do. Now you add a cell to your cell complex, and if you add a cell, then the space of maps will be a fiber over previous space with space of map from a sphere. And then by exact sequence, you add kind of one cell multiplied by homotopy groups, and you shift by dimension of the cell. Yeah, so it really looks it should be some kind of spectral sequence. In topology, it kind of works when you have this restriction of dimension. But if restriction dimension are not satisfied, you will see some kind of nonsense, because here in this tensor product you get pieces in cohomologically positive degrees, which shouldn't exist in topology. So topology kind of truncate this part, and you get something not so clean. And what I claim that it's this description of space of deformation complex, it's more or less the same picture, because this G can be thought of as cells, and this can be thought as homotopy groups, and this you get again like homotopy groups of the space of maps. Yeah, so that's a good analogy to see this topological situation. Okay. Yeah, so we can deform morphisms. And I will return later to this picture. But also we can deform algebras as well. It's the deformation theory, deformation complex of algebra. Let's suppose now we have just algebra B. How we make deformation complex with this algebra? We replace by resolution. And consider derivations of resolution. Is a DG algebra. G. And now, as a vector space, it's essentially like home from G to A. As a vector space, as a graded vector space. Now we shift it by 1, and it will be DG algebra. In particular, will be infinity algebra, and it will have this deformation theory as well. Is deformation complex. Yeah, so it's, there is this picture, but now we can see that if you compare the answer versus the vector space, you see that it looks like more or less the same story here. In fact, it's this deformation complex of algebra, or maybe of B, it's more or less the same as deformation complex of identity morphism. But this is deformation complex of identity morphism shifted by 1. Yeah, so we get identification of two equations, deform algebra itself or deform identity morphism. And that's will be a major tool, what I will explain. Yeah, so that's essentially all what one should know about deformation theory. One should make some kind of resolutions, and the good resolution, bad resolutions, and try to calculate the Lie infinity algebras. Now I return to my main object of interest. Oh, no. Oops. Sorry. So it was descent. Right now we have to make some kind of, again, some intellectual leap. We consider deformation theory of operad of Gastro-Hyper algebras. So what I'm talking about? I was talking before talking about deformation of algebras, but now consider deforming operad. How to handle this in your head? The operad, what is an operad? It's a collection of representation of symmetry group and bunch of maps. So it's many vector spaces. For example, for each Young diagram, we get certain vector space corresponding to reducible representation of fundamental group. There are situations in algebras when we can speak about these operads which we are talking about. It's about one vector space, but one can speak about two vector space, like algebra and module. This situation we have two vector spaces interacting in some way, so it's called colored operad. When you get several types of vector spaces, one can have infinitely many types of vector spaces as well. And in particular, operads themselves will be algebra of something called over some colored operad. Yeah, so it's some kind of fun to understand what is going on. Operads are algebras over certain colored operad. And this colored operad has which made from collection of vector spaces, a collection of representation of representations of symmetry group, which produce a new collection of representation of symmetry group. And in general, the picture is like this. What you do, you draw all possible trees and put your spaces with your operad here and here, here and here and here, take it as a product and mod out by symmetries of the trees. Yeah, so one can kind of handle in your head what is operad corresponding to notion of the operad in one of kind of one color to operads. Yeah, so that's so the question we shall discuss what a deformation theory of the Gastro-Hyper operad. So how to handle this question? According to general recipe, we should find a free resolution of this Gastro-Hyper operad. And the good fact is resolution of classical operads which have names are known explicitly. Yeah, for example, if you want to consider operad of associative algebras, those resolution called something called A-infinity algebras. And the space of generators is something like this. You get associative n and shift by n minus 1. You consider the space of generators and maybe n minus the second. I think maybe n minus 2. Yeah. And the same happens. It's essentially classical calculation from maybe even late 60s by Moore. That for commutative operad, for commutative you get some commutative infinity resolution commutative infinity algebras, and generators will be Lie, again shifted by n minus 2. For Lie you get commutative shifted by n minus 2. And for Gastro-Hyper algebra you also get up to shift Gerstenheimer algebra. So Poisson is dual to itself, and Gerstenheimer is dual to itself. Yeah, so there is a simple explicit resolution which you can write for this Gerstenheimer algebra operad. And in fact, maybe I should put here dual spaces. And in particular for Gerstenheimer operad, because it's dual to itself, generation will be dual. In Kosul duality, yeah, so this free resolution will be generated by more or less the same spaces. What you get deformation theory of Gerstenheimer operad. It will be up to shift. You get the following graded space. You can see the product of all n greater than 2, where n multiplied by where n is n 4 minus 2n shift by something, and it will have some complicated Lie infinity structure. So you get up to shift. You get this. Here are the resolutions, and here is the operad itself. Yeah, in this case, it will be Lie structure. Yeah, for Gerstenheimer, it will be Digital Algebra. It's actually not complicated. It will be G. No, actually, no. This complex kind of there are two complexes. There's complex of deformation of identity morphism from operad. Then you get simple Digital Algebra structure. But deformation of operad itself, it's a complete mess. Yeah, I mean deformation of operad itself. Yeah, so it will be Lie infinity, complicated Lie infinity structure. Now, and that that's essentially an object which Willwacher somehow not calculated but reformulated to completely different type of complexes. Yeah, so you don't see this Gerstenheimer thing itself. So why this thing is related to kind of circle of equations called Grothendieck-Teichmüller group. So this the whole story is pretty complicated. First of all, I just want to say this kind of very important observation that if consider nth component of Gerstenheimer algebra, it's some z-graded space. I claim it can be naturally interpreted as homology of configuration space in Cn or maybe R2 Rn in two-dimensional space. And all structure of operad one can see from this description. This is something called little two-disk operad. Instead of this space, one can consider space of configuration of n disk in a standard unit disk. It's some topological space. And this space is form a topological operator, but because inside of one picture one can put smaller copies of another picture, it will be like a periodic composition. Yeah, so it's come from topological operad. It's homology of a topological operad. And because it's homology, these spaces are not just vector spaces, they are dual co-homology, and homology is commutative algebra. So it's commutative co-algebras. So it's operate in the world of commutative coalgebras. So one can try to define, but it's extremely heavy to write, to put on a paper, what is deformation theory of this thing as operator of co-commutative coalgebras. It will be some even more complicated business. But this operator of co-commutative coalgebras. In fact, Willwacher, one of the results of Willwacher, he wrote some kind of explicit formula for this deformation theory of this is co-commutative coalgebras, and the answer is pretty neat. Namely, you consider you get the following guy. It's a product in n greater than 2. Consider ger n multiplied by something called Tn. So just now make a different shift. Where Tn is a Lie algebra generated by it's called Drinfeld Lie algebras. It generates Tij equal to Tji, where I is not equal to j from 1 to n. And the relation is that Tij Tjk is equal to Tjk Tka for any ajk, and Tij Tkl is equal to 0 if ijkl distinct. So it's certainly algebra. What is this Lie algebra? It's actually a rational completion of the fundamental group of this configuration space. It's a braid group, yeah. It's a braid. Yeah, infinitesimal braid group, yeah. Yeah, so it's essentially kind of fundamental group. And this space has only one group, it's fundamental group. And this is homology, or dual to cohomology, because by Poincaré duality. So you see that we see here essentially the same picture which I explained to you in topology. Multiply homology by homotopy group. It's only one homotopy group here. Yeah, it's a different complex. It's a smaller complex than this one, and it's responsible for deformation of this thing as.
And the shifting degree is 5?
5, yeah, because it's pi 1, so it's yeah.
And the other one was 9.
4. Yeah. Yes. Now, so that's all. Actually, a bit short on time. Yeah. So you get this differential theory, and there are many details here, but that's essentially express the idea of Grothendieck that Galois group acts by symmetries of braid groups in some compatible fashion. And this compatible fashion will be compatible with operatic structure, which is not precisely what Grothendieck means, but pretty close. And then this thing should be called, it's kind of DG algebra, which is automatically in non-negative degrees, because this by shift you get something in positive degrees here. And in degree 0 will be should be symmetries of a tower of this infinitesimal Lie algebras. Now, so it's kind of very theoretical up to now, but sorry? Sorry?
The law
Yeah, Galois group acts, for example, on L-adic completion on braid group. And you get, of L-adic numbers, you get plenty of symmetries of braid groups, of completed braid groups, compatible with this operatic structure. Galois group of Q bar or Q, because the spaces are modular space of configuration space of points in C, just algebraic varieties over rational numbers. Yeah. 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 So get this Galois symmetry. Sorry? Yeah, on profinite completion it's phase selection, but on L-adic completion nobody knows. It's yeah, that at least one sees that zeta of 3 and so on by symmetries of these pro-nilpotent completions. Yeah. So what is kind of progress here? We get Lie algebra in non-negative degrees. In degree 0, cohomology will be, if one analyze the story, exactly definition of Drinfeld. So definition of Drinfeld will be some solution of some complicated system of equations, the symmetries of braid group. And it will be only 0 cohomology of some long complex. So it will be kind of resolution of Drinfeld description in a sense. So that's why one can call it derived Grothendieck-Teichmüller Lie algebra. And this is a huge object, and it's extremely hard to do any calculation because all this Lie bracket, all very messy. And the kind of major result of Willwacher is that he identified it with something which came also about quite a long time ago, 25 years ago, something called graph complexes, which has no this Gastro algebra in it at all, and no the standard product description. I'll just tell you. What are these graph complexes? Yeah. Yeah, it's a certain Digital algebra, so no complicated higher brackets. It's called graph complexes. So the definition of this Digital algebra is very simple. You start, gamma will be finite connected graph. And you enumerate edges. Graph could be like this, doesn't matter. Just any finite connected graph. You enumerate edges and associate to this certain vector in this graph complex. If you enumerate edges, kind of E1, En, we have edges. If you make a permutation of enumeration, you multiply by -1 by the sign of permutation. Yeah, so if a graph has automorphism which gives odd permutation of the set of edges, it will produce 0. And you define differential of this graph in the following way. Just take sum over all possible vertices, and you try to blow up one edge inside. There are finitely many possibilities. You just decompose a set of half edges by two parts. Take sum of all, blow up, and add a vertex to add new edge. Sorry? I consider space of linear combination of these graphs. Okay. And for each graph, we get, by blowing up, we get finitely many terms. And this square will. Oh, yeah, finite linear combination of graphs. Yeah, yes. And the differential is given by this procedure. And this square equal to 0 because this ordering of edges. Yeah, so it's a very simple complex. And it actually has a structure of Lie algebra. And differential should be commutator with after isomorphism. Yeah, I consider yes, and with enumerations and with this relation. If you change enumeration by permutation multiplied by sign. Yeah. So I get this this complex, and there is some Lie bracket here. Will be kind of anti-symmetrization of certain insertion operation, and insertion operation is the following: you take graph gamma 1, remove some inside one vertex, put some graph gamma 2, and try to connect in all possible ways edges. It will be some non-symmetric operation, non-skew-symmetric operation. You skew-symmetrize it to get Lie bracket.
Notation is a pre-Lie algebra, I suppose.
Yeah, this is pre-Lie algebra, yeah. Yeah, so you get pre-Lie algebra and you get this Digital algebra. And commutant is, the differential, in fact, is commutant with this graph. It's very easy to see. Now, so you get this graph complex, and the claim that the story up is essentially graph complex. Yeah, which is completely surprising because we start with this Gastro algebras, which has nothing to do with graphs a priori, and the description is like product of two Gastro thing. So I don't have really time to explain this. With the proof of Willwacher, when I started to read it, I was very tired. It was something maybe 100 spectral sequences. On each page there are 2-3 spectral sequences all the time. That's a kind of rehashing. But eventually, in the text, I kind of extracted the idea. It's really short, simple proof, but goes through some. There are several intermediate steps which I don't have time to explain. Just I want to. So what are corollaries for this result? First of all, we get something when we explicitly have Lie bracket and not complicated things like in Drinfeld description. Also, these graph complexes are finite dimensional. If you fix earlier characteristic of the graph, there are only finitely many graphs. Essentially, all three parts is irrelevant. We get some finite complexes, and which gives you some vanishing of some weight components of this Digital algebra of this derived Grothendieck-Teichmüller group, which you cannot see a priori from other description. In other things, you get unbounded complexes in each weight, and here you get bounded complexes in each weight. On the other side, it gives information about graph complex because the whole story says that it's cohomology, because the cohomology of things are only in positive degrees. Then you see that it's for kind of half of possible degrees, the cohomology of graph complex vanishes. Yeah, so so information goes both ways. And also in the graph complex, it's very hard to do any calculation. Yeah, so there was some calculation about 2000 by Bar-Nathan, which seems to contain mistake. And recently, Willwacher calculated earlier characteristics. And it looks this graph complex will have something beyond Grothendieck-Teichmüller group. Definitely, it will be something in so what literally says that should be some natural operation of, let's say, cohomology of modular space of configuration space.
Where is the log group X in these terms?
Sorry?
Where is X? The log group X of the homology of this?
No, something called some Mathieu Galois group will map to some zero cohomology in certain sense of this graph complex. But what we'll see something not coming from Galois group at all. And what is it? It's these are operations on cohomology of modular space of the genus zero curves, for example, compatible with all operatic operations, which do not preserve degree in cohomology but raise degree in cohomology. And it's a very interesting question because all theory of motives by Grothendieck was he thought about like Galois group or hot structures, things which exist, some structures which exist on cohomology in given degree, and you try to see what are all universal operations acting on cohomology on given degree, also algebraic varieties. In topology, we know that if we consider cohomology with positive coefficients in finite fields, then there are standard operations which raise degree. And so that raises the possibility that there should be operation cohomology of algebraic varieties which raising degree. Not preserving degree, but raising degree. Yeah, so it's a completely open question whether such thing exists. And there was a proposal by Joseph Ayoub about kind of, again, derived motivic Galois group, which also includes operation of which raise degree in cohomology. And just final examples. So the simplest graph which gives a cohomology class is this graph, which produces all formulas from which I started in the beginning for zeta of 3. Yeah, and this is kind of zeta of 3. Zeta of 5 corresponds to something more complicated. It will be graph with 5 loops plus something, whatever complicated, I forgot, some kind of linear combination.
In what sense?
Sorry?
What is correspondence with zeta in this graph?
The story is the following. The motivic Galois group act on cohomology or rational homotopy type of configuration spaces. And we know essentially this section by many means, and they relate to multiple zeta numbers. And this corresponds to multiple zeta numbers will be like functions on the corresponding group. And in this graph complex, it will be a completely different picture how we see these elements instead of this complicated derivation of braid algebras. We just draw these diagrams, which again known only maybe first 2, 3, because it's horrible computer problem. And so that was the origin of the first formula in certain sense, and this gives some analogous formula for high flows acting on Poisson brackets, for example, in our situation. Yeah, so this derived Grothendieck-Teichmüller groups acts on plenty of stuff. So it acts on this deformation quantization question when you try to quantize manifold to take Poisson brackets, it acts there. Also, it acts on things one can describe in some universal way homologous space of embeddings of sphere to another sphere of light dimension. This is all again described to this graph complexes, so it's kind of completely.
Cohomology with space.
Yes, yeah. So that's maybe all. Yeah, thank you. Yeah.
Est-ce qu'il y a d'autres questions ou des commentaires?
This graph, which appears as Feynman graphs and have the same residues, theta 3,
Yes.
5, you have for 4 loops zeta 5. You don't have to increase by 2 loops to get zeta 5 for Feynman graphs.
No, I think it's these are different from calculation. There is a way to associate two graphs numbers from this quantum field theory, but there is an important difference. When you consider graphs, you don't order edges after permutations. And so it's a different story. But in a sense, closely related. Yeah, it's the story of Poincaré. It's 4-dimensional field theory. It's 2-dimensional field theory. Sorry?
Field theory.
Sorry?
Zeta 3 is there. For
yes,
this
exactly.
Graph.
Yeah. The story is the following. It's actually this diagram, but in 2-dimensional field theory, not in 4-dimensional field theory.
Also in 4-dimensional.
No, but my story it's related to 2-dimensional field theory because the configuration points in the plane.
Je crois qu'on peut remercier Maxime.